Good afternoon, my dear students. Welcome to the digital electronics class. Am I audible? Hello. Please respond.
Yes, sir.
Yes. Oh, okay. Are you able to see this text read-only memory title? Is it properly shared? Hello? Hello?
Yes, sir.
Oh, okay. Right. Now I will discuss about read-only memory. This is one type of memory. Actually, memories we have two types. Okay, one is random access memory. Random access memory, RAM. We'll say this is called RAM, RAM. So another one is read-only memory. Okay, read-only memory. Okay, in the random access memory, we have two operations. We can read from the memory. We can read the data from memory. That means we can extract the information stored in the memory device, and also we can transfer the data into the memory. That is write operation. Okay. Transferring the data into the memory is considered as write operation. Extracting the data from the memory device is known as read operation. So now our focus is on read-only memory. Okay. Now today in this session we will discuss about read-only memory. In this, the data is already stored. Okay, and it can provide the data required. Okay, that means we can only read the data. We cannot change the data. Okay, after reading the data will not be altered. Still the data remains permanently. Okay, that is ROM. Okay, read only memory. So it only read operation is there. Okay, so writing means at the time of manufacturing the device, certain some required information is embedded in the device at the time of manufacturing the device. Okay, so once manufactured the device, the data cannot be altered. We can only read the data from the device. Okay, it's block diagram. Let us say block diagram. I will show you the block diagram. So we are focusing now on ROM. Okay, read only memory. This one. Let us focus on the read only memory. Don't forget about the random access memory, RAM. Forget about the RAM. Okay, that is not there now. Okay. Now the block diagram of the RAM. I will show you the block diagram of the ROM. Okay. It consists of some number of inputs, say some k number of inputs. Some inputs, okay, some k number of inputs. and n outputs. Okay. Here these are the inputs. Say for example, k ankondi. Okay, k inputs. K means number of the inputs. Okay, let us say k inputs are there. Okay, so these are the outputs. Outputs can be any number. Inputs can be also any number. Okay, that is here n outputs. N outputs. Right. Okay. So here this is known as with the help of k input variables. How many inputs it will represent? How many entities it will represent? Each variable, each input assumes either 0 or 1. Now we have k inputs. So how many total number of inputs combinations are possible? Tell me. How many number of input combinations are possible with k? Suppose with two inputs, say for example with x, y, how many inputs are there possible? 0, 0, we can take 0, 1, 1, 0, 1, 1, like that. Okay, with the two inputs we have 4 combinations, no? Similarly with three inputs x, y, z, for example,
2 power k.
right. So you got the point. Okay, so with 3 inputs you have 8 inputs. Okay, 1, 0. Just okay, because after a long time we are meeting, so just I will show you. So like this, you have okay. So see, you have got the 8 combinations here with 3 inputs, like that. So in general it is 2 power k. Correct, you are correct. Okay, 2 power k combinations are there, input combinations. Here outputs are n output. So it can be specified, this device can be specified as 2 power k by n ROM. Okay, 2 power by ROM. Okay, so this size of the ROM is mentioned like this. Okay, 2 power k by n. Right. Let us take one example. Okay, this is in general the block diagram. Okay, and this can be also very simply, this can be also shown like this. For more clarity, it can be shown simply like this also. You can show like this also simply. Okay, instead of showing all these multiple number of input representations, can be represented with single arrow. Okay, right. So here it is k inputs, you can write like this. So this is k number of inputs. Some disturbance is coming, Babu, please take care. K inputs and here n outputs. So like this also simply you can represent 2 power k by n ROM. Right. So this is the block diagram of the ROM. Right. Now let us take one example. You have seen the block diagram. Now let us see the example. Consider, for example, here 2 power k and n something. Let us take 2 power. Suppose say k is equal to, let us say, some 5 inputs. K means 5, for example. 5 inputs. Okay, example. So what type of let us say n is equal to, say, something. Okay, n outputs. Let us say n is something, say 8 or something. Okay, 8. Okay, in this case 8. So outputs. These are the outputs. Right. K is equal to 5. These are the inputs. Right. So what kind of ROM we will get here? So 2 power 5. That means you can write like this. 32, no? 2 power 5 means. So you can mention like this: 32 by 8 ROM. Right. So here 5 inputs are not. Okay, 5 inputs are there. Here we have 5 inputs. Five inputs are there, and here these are n outputs. Okay, that is 8 outputs. Okay, yeah, 8 outputs. So we can also we can replay now. For more clarity, I will show like this. For more clarity, I will show. Five inputs. 1, 2, 3, 4, 5. 5 inputs. Okay. 8 outputs. 1, 2, 3, 4, 5, 6, 7, 8. Right. Hello, from someone. Noise is coming, please. Right. This is a same thing. I'm just, for more clarity, I am drawing like this: 32 by 8 ROM. Right. So with 5 inputs means there are 32 memory locations are there. Okay, and 8 means the 8 outputs means each word. Okay, each data consists of 8 bits. That is the meaning. 8 bits. Okay. For example, here suppose say we are having the input variables like this: v, w, x, y, z. Okay, please just a minute. Okay. So here the outputs can be, say for example, it can be like this: A0, A1, A2, A3, A4, A5, A6, A7. Okay, right. So with the help of these input variables V, W, X, Y, Z, okay, we can read any word among these 32 words. Okay, that is here this 32 by 8 ROM is able to store 32 words. Okay, what is the meaning of this 32 by 8 ROM? Means ROM consists of 32 words or bytes. You can say 32 words, different data, 32 words. Each word of 8 bits. Each word consists of 8 bits. That is the meaning. That is the meaning of this specification. Okay. So there are 32 words in this. Okay. Now let us see how is the structure. How is the internal logic diagram of this 32 by 8 ROM? Okay. See. Before this, I will show you one important convention. Some important convention that is used in the case of programmable logic devices. Actually, our unit title is programmable logic devices. That is as per our syllabus. Just I will show you. Okay. See here, design of combinational circuits using programmable logic device. Are you able to see the syllabus paper? Am I sharing properly or not? I am checking myself. Please tell me. See the syllabus. Hello? Hello? Hello?
Yes, sir. Yes, sir.
Okay. Now this is the design of the third unit. We are in the third unit. Design of the combinational circuits using programmable logic devices. Okay. In this, ROM is one important programmable logic device. Okay. It's basically a combinational circuit constructed with programmable logic devices. Okay. Now, right. So I will show you the structure. Before that, I mentioned one important convention is there. How the logic symbols, logic gate symbols are used here in this case. Okay, here we have a new type of representation is there. I will show you. See, normally you know that say some OR gate is there, for example. 4 input OR gate, for example, you consider like this. 1, 2, 3, 4, like this. Okay. C, W, X, Y, Z. Okay. So this is some output. Okay. Here. These are the inputs. Okay. Right. Output you can mention some say Q and some not. So this is called conventional symbol. Conventional logic symbol for OR gate. Okay. Generally here for array logic, and we are now programmable array logic, programmable logic arrays. Okay. Programmable logic devices consists of PAL, PLAs, complex programmable logic device, all this. Okay. Here we have different kind of symbol. One simple line, just simply here one line and here another line. And here, so W, X, Y, Z, no? So 4, these 4 vertical lines. That's all. Okay. So here this is a W, X, Y, Z. That's all. Okay. So it will be represented like this. Okay. Because this is convenient. This kind of symbols are used here. In this case, we have large number of input variables. For example, some 20 inputs are there, for example. Suppose we have 20 inputs, okay? Let us say here, this is x1, x2, like this. Suppose we have some 20 undachu, or let us say this can be say for some 100 undachu input variables. Suppose say. Now, in this case, we have very simple representation. One line, and we have number of vertical lines. 1, 2, 3. 100 variables are there now, so we have 100 variable, 100 vertical lines like this. Okay, that's all. So that is here. This is x1. This is x1, x2, like this, x3, like that. Okay, so this is x99. This is x100, like this. So this is the called array logic symbol, array symbol. Okay, whereas this is a conventional symbol, conventional logic symbol. Okay, yeah, this is a conventional logic symbol. This is conventional symbol for logic gates. Symbol for logic gates. Okay, whereas this is array logic. Okay, array symbol. Array logic symbol for OR gate. Okay, array logic symbol for OR gate. Okay, okay, symbol for OR gate. Okay, similarly for AND gate also you can draw. Okay, right. Now let us come to our actual 32/8 ROM. Okay, where is it? Okay. Let us see. I will take some pages. Please wait. Okay, okay, pages are there, right? So we have 5 inputs. So 32 words will be there. 32 locations will be, memory locations will be there. Okay, so this is 1, 2, 3, 4, 5. Next, here we have different locations. Okay, one is memory location 0, 1, 2, 3, 4, like that. We have up to final one is 31. Okay, we have all these are the outputs of the decoder actually. Okay, so ROM consists of one decoder and external OR gates. So here 1, 2, 3, 4. Yes. Here it is 30, 29, 28. So we have 32 locations are there. So few of them are being shown here. Right. This is simply a decoder circuit. Okay. This is a decoder device. Okay. So it is a 5 by 32 decoder. 5 by 32. 5 by 32 decoder. Right. So here these are let us say input variables v, w, x, y, z. So we have these 32 outputs. Okay, from the decoder. Okay, that is this decoder is specifying to the 32 locations of the memory. So in each location one word is stored. Okay, right. And next. So here we have one OR gates. One, two, three, four, five, six, seven output, 8 outputs. No, so 8 OR gates. It consists of 8 OR gates. 1, 2, 3, 4, 5, 6, 7, 8 OR gates. Okay. So how these are, for example, in 32 locations, suppose we have different types of information, for example. So all this, each output of this decoder is connected to the one of the to every one of the OR gates. Okay, OR gate inputs. Okay, there will be connection here. So like this. So now here 8 OR gates and here 32. Okay, between 32 and this 8 inputs, how many total connections will be formed? Tell me. 32 into 8. Tell me how many connections are there? 32 into 8, that is 256 connections will be formed here. Like this. Okay, so during the manufacturing process itself, we have connections. See, from this 0th location and from location 1, location 0, location 1, location 2, location 3, all these are the outputs from the decoder. Okay, all these are connected to the to this external OR gates. Okay, OR gates. Okay, actually not external. These OR gates and this decoder, everything, this entire thing is available as one structure inside the ROM. Okay, so I will note down these points. Okay, let us say here this is, let us say A0, this is A1, A2. So output is available here in the form of bits A, A4, A5, A6, A7. Okay. So here, for example, in this device, I will take one more tool. Right. This entire thing is like a ROM structure. At a MIG, what you will see, just you will see the 5 inputs variables and 8 output variables. Okay, this entire thing is inside the ROM device. Okay, so ROM consists of a decoder and built-in OR gates. Okay, depending upon the structure. Okay, how many number of OR gates are there here? 8, because we have 8-bit word. Okay, this ROM is providing 8-bit words. Okay, how many such kind of words are there? 32 words. So this entire thing is the ROM. Right. What type of ROM is this? This is 32 by 8 ROM. So this device consists of 32 words of each word of 82, each word of 8 bits. Each word of 8 bits. Okay, right. In order to address the 32 locations, we require 5 input variables. No, 32 32 locations are there. So in order to represent 32 different symbols, 32 different locations, we require 5 input variables. So we address lines and under K, E, V, V, W, X, Y, Z. These are called address input lines. We can say, we can also say address bits. We can also say address bits. Address inputs, address inputs, actually. Okay. Okay, let us see, suppose for example, what kind of information is available. Okay, ROM can be specified in terms of truth table also. Okay, ROM can be also specified. Ikkademo just block diagram icham ROM truth table and information, complete information is available about the ROM. Okay, truth table. Okay, ROM truth table. I will show you now. ROM truth table. Okay, so here so we have 5 inputs, no? So let's just say VW XYZ. Okay, VW XYZ inputs. Okay, and these are the inputs and outputs. Let us see outputs. A7, A6, A5, A4, A3, A2, A1, A0. Okay. So these are the inputs. These are the inputs. These are the outputs. Okay, inputs, inputs, outputs. Inputs, you know, how many combinations? 32 combinations, starting from the first address. Okay, 0, 0, 0, 0, 0, 0, 0, 0, 1, like this, 1, 0. Next 1, 1. So like this, we have 32 address locations, right? Last, okay, let us say here. Finally, it will be 1, 1, 1. Okay. Oh yeah, just before this, like this, no? And before this, here I will take 0, 1, 1, 0, like this. So like this, we have, no? So this is 28 to 29, 30, 31, like this. Okay. So this is 28, this is 29, 30, 31. So like that. So we have 32 address locations, 32 addresses we have formed. Okay. With the help of 5 input variables, 32 addresses are formed. Okay. In each, okay, each combination means each, this is one address. Okay. So it represents particular memory location. And in that memory location, whatever, just a minute, please, just a minute. Oh. Just a minute. Next, so here we can have any kind of data. For example, in the memory location which is specified by the address 00000. Suppose some data is there. What kind of data? Suppose say, let us say, for clarity, I will show you for interesting point of view. For example, some ASCII code. Okay, for example, some different letters. For example, here some letter is represented. Say, for example, R is represented here. For example, okay. Suppose say R. What is the ASCII code for R? Okay, what is the ASCII code for R? Okay, I will show you. You can check that letter. Okay, ASCII code for the letter R is a or let us say some P. I will tell you some letter. Some letter P. Okay, let us say I will show here in the memory location 0 we have the alphabet P, for example, and in the next memory location we have Q, for example. In another memory location we have R, for example, R, S, like this. So for P we have the ASCII code. This is 50. Okay, in hexadecimal it is 5. Hexa, H I will write here, hexadecimal representation. So like that, for this Q you have 51. H, and for R it is 52. You can check this. This is ASCII code for the alphabet R. Similarly, for alphabet S we have 53H. Right? So 50. How do you write to 50? And ASCII code requires only 7 bits. Suppose if we follow some even parity, so that means the 7th bit can be used as a parity bit, for example. So we will fill up this latter parity bit, for example, just for, okay. I'm representing some alphabets, some text with the help of ASCII code. ASCII code actually requires 7 bits only, but if you want to have some kind of parity bit also is entered here. So that is A7 bit, A7. Okay. First of all, 50. How do you write 50? 1 0 1 0 0 0 0. Right. Next to 51. How do you write? 1 0 1 0 0 0 1. 52. 53. So this is 50, 51, 52, 53, like this. Some data is available in this memory location. And here I will show something, whatever it is. Okay, for example, if I maintain even parity, I will show like this. This will be 0. This will be 1. Some even parity. I want to store the data with ASCII code with even parity. So 1, 0. So like this. Similarly, in this also some data is available. For example, let us say here something, whatever it is. Let us take some numbers. Let us say here in this location, some numbers are stored. For example, something suppose say some 1, or let us say 2, 3, 4, some numerical information. Okay, for 1, what will be the ASCII code for 1? It will be from the ASCII code table. From the table of ASCII code, I will show you. It is 3, 1. It is 3, 1. So for this, we have 3, 1. So for this, we have 3, 2, H. 3, 3. This is 3, 4. So 3, 4, H. Oh. So here it will be 0, 1, 1, 0, 0, 0, 1, like that. So next 0, 1, 0, 0, 1, 0, 0, 1, 1, 3, 4, 0, 3, 1, 0, 0. Suppose I am maintaining the even parity, no? So what could be the 7th bit here? Tell me, anyone, please. Here it could be, it should be 1. Here it should be 1. Because we want to make the number of ones in each representation equal to number of ones should be even. So here it is. Please tell me what should be the 7th A7 bit here. 0. Here 1. No. So this kind of data is stored in the. So and in between I am not showing. Okay. So some first 4 memory locations, whatever is stored, first 4 address locations, what data is stored. So here in the address location 0, a letter P is stored. In the address location 1, memory address location 1, Q, alphabet Q is stored like that. Alphabet R is stored in the memory location 2, like that. Okay. Right. So I will mention memory locations for more clarity. So memory locations we have. So this is 0, 1, 2, 3, like that. This is 28, 29, 30, 31. Okay. So address locations, right? So this is actually data. Data available, data stored in the ROM device. Okay. Data stored inside in the ROM. In the ROM. So how the manufacturer will store this information? Let us see. Okay. So structuring the links. Wherever there is 1. Already here 256 connections are there. All these through 256 connections are established during the manufacturing process. Wherever there is 0, in that place, that connection is removed. Wherever 0 is there, in that part, connection is removed. Here, see, say in the first place location, at A4, at A5, A3, A2, A1, A0. Please wait. Right? Now the question is how the manufacturer will store this information. Okay. Any doubt, please? Any doubt? Are you following? Actually, very simple information. Okay. Any doubt? Please stop me. You will come to know the actual. So this is called ROM truth table. Okay. So complete information about that ROM is available in the form of truth table. So what you will understand in this truth table, that means here this data is available in the ROM. What data? Here it is shown in terms of bits A0, A1, A2, A3, A4, A5, A6, A7. So what kind of data here I am taking? I am showing you some letters here, some alphabetical information, textual information, P, Q, R, S, for example, like that. Similarly, some numerical data, 1, 2, 3, 4 is being stored here. Okay. So structure during the manufacturing itself, this data is embedded. I will show you now. Right here itself, I will show. For example, so wherever there are 1, I will represent with cross symbol, X symbol. That is at A6 and A4. You have crosses. We have one cross A6, A4. Student first the P. Ekla the A6 ki 1, A4 ki 1 undi. Remaining all other A bits are 0. So what I will do, A4, A6, first I will prepare A4. A4. Student ikkada. Chala simple ikkada mottam logic. A4. So ikkada connection is there. A4 is 1. So I will put here one cross here. And A6 also. Just a minute. Right. So at A6, just a minute. Oh, sorry. Let's take this one. Right. Next A6, A4, we have 1. So at all other places 0. That means here no cross mark means there is no connection. Let us think like that. Next in the address location 2, what is there? A7, A6, A4 and A0 all are 1. Remaining are zeros. That is first I will mention. Okay, A7, A6, A7, A6, A7, A6. A7, yeah, this one, A7, A6. ఇంకెక్కడ ఉంది 1 చెప్పండి. A4 and A0, A4 and A0, A4, A0, right? Next, at output of the, that is output of the decoder denoted as 2. This is as the connections to A7, A6, A4, A1. Okay, so A7, A6. First, let me repeat: A7, A6, A7, A6, 7, A6. Next, A4 and A1, A4, A1, A4, A1 అంటే ఇది. Next at address location 3 specified by 3. ఇక్కడ ఏముంది? A6, A4 1 ఉంది. A6, A4, A6, A6, A4. అంతేనా? ఒకసారి let me check. At address location 3, A6, A4, correct. And A1 and A0. A1 and A0. A1. A0. Right. ఇక్కడ కూడా ఇట్లా ఉంది కనెక్షన్. ఇవన్నీ ఫ్యూజెస్ అన్నమాట. యాక్చువల్లీ ఆల్రెడీ అన్ని ఫ్యూజెస్, ఫస్ట్ ఆఫ్ ఆల్ దిస్ క్రాసెస్ అన్ని ఎట్ ఎవ్రీ పాయింట్ క్రాసెస్ ఉంటాయి అన్నమాట. ఓకే, సో ఎక్కడైతే మనకు వేరెవర్ దెర్ ఇస్ జీరో, దట్ క్రాస్ ఈజ్ రిమూవ్డ్ అన్నమాట యాక్చువల్లీ. నెక్స్ట్ ఇక్కడ ఫస్ట్ 4 చూపించాను, లాస్ట్ ఫోర్ చూపిస్తాను. ఓకే, సో ఎట్ 28th లొకేషన్, memory location 28th, between the memory location 28 and outputs, what are the connections? So A7, A5, 4, 7, 5, 4, 7, 5, 4, 7, 5, 4, 7, 5, 4. Next, 5, 4. ఇంకెక్కడ ఉంది? A0, అంటే A0. నెక్స్ట్ ఎట్ 29th దగ్గర ఎట్ A7, A7 and A5, A7, A5, A7, A5, A4, Next, at A1, If you understand this one, the entire ROM can be good understanding you will get, okay, with this structure. Next, at 30, at the memory location 30, we have, this is a 6, 7, A4, 5, A4, 5, 4, 5. Next, A0, A1, A1. Next, A1. This is over. Next at 31, the location A7, A45, A7, A7, 45, and A not A1, A2, A2, A2. Sure, C. So when we have the memory location, if the memory address 00000, what happens? The decoder output except 0, all others will be disabled. So only this at 0 you have the logic 1, and in that what are the connections? The connections are made to the A6 and A4. So except A6 and A4, all others remain as 0. So what will be the data you will see at the outputs? So 0, 1, 0, 1, 0, 0, 0, 0, like that. So that data will appear here. So when I mention 0, 0, 0, 0, 1, in that case, so what data I will get? 1, 1, 0, 1, 0, 0, 0, 1, like that. Okay, so this data will appear in that location. See, so during the so like this. So here in this 32 memory locations, we have shown first four data 4 lo, and last 4 lo chupicharu. Okay, first 4, last 4 I have shown you. Okay, data. This is called truth table. Just a minute. Just a minute. Next, next programming the RAM was shown to you. Okay, here this is called programming the RAM. Okay, according to the data. So programming here means it is a hardware procedure. Here it's not a software procedure. Okay, here the programming here means actually, strictly speaking, it's an hardware procedure. Okay, so only during the manufacturing itself, this ROM is programmed. Programmed means these connections are established during the manufacturing process. Actually, here we have 256 connections, no? So 256 fuses means this connection, you know, no? Fuses. like electrical fuses. Okay, so 256 fuses are established and sometimes it is customized. That means the customer, that is a designer, okay, he can just simply order the size of the ROM, okay, while during the ordering process 32/8 ROM annukondi. So 256 connections will be provided. Suppose the customer wants to store some information, say this, the PQRS like this 1 2 3 4. So at his location, the customer can program the ROM. That is wherever zeros are required. So in that point, fuses will be blown, that is eliminated. So 0 one matter here. See, so here cross mark indicates fuses are maintained. So in the beginning, the manufacturer will provide with all the 256 fuses intact. Readily fuses. All the 256 fuses will be available. So user, suppose I am a user, I want to save some information in this ROM device, certain kind of information I want to store. I can store information of my interest. Okay, so by blowing the fuses which are not required, by keeping the fuses intact as it is, whichever are required. So like that. Okay, so that is called programming the ROM or OM. So this is one point. So here the programming the RAM means it is an hardware procedure. This hardware programming consists of blowing the fuses when the connection is not required and keeping the fuses when connection is required. That's all. Okay, wherever connection is required, the fuses will be kept as it is. Wherever connections are not required, fuses will be blown. That is, connection not required means 0. Zero. So this is one thing. Right. Here you can also treat this ROM as a combinational circuit consisting of 8 outputs. Put A0 one output, A1 one output, A2, A3 like that. Okay. So atla kuda we can visualize. Okay. Right. So this is about ROM. We will take one example. Implementation of any combinational circuit with the help of ROM. Implementation of any combinational circuit with the help of ROM. Okay. Now I will show you. See, after a long time, so please wait for some time. Okay, we have to spend some more time. Okay. Any doubts? If you have, please ask. Up to here, any doubt? Yeah. Now let us see one example. Right. Combinational circuit implementation. Let us implement any combinational circuit. Here, ROM can be visualized in a different way also. Okay, as a combinational circuit. Okay, as a combinational circuit. Now, how here A7, A6, A5, A4, A3, A2, A1, A0, they are treated now as switching functions. So in that case, A7 can be written like this. A7 can be, see, I will write A7. A7 can be represented like this. See, is a switching function consisting of, depending on variables. See, A7 is one switching function depending on B, W, X, Y, Z. Okay, as sigma. See, this is min term. So that is 1, 2. So in between we don't know. So that's why what I will mention. So like this I will mention. like this I will mention, and finally here 28, 29, 31, like this. Okay, so this is one switching function A7. So it is sum of the minterms, that is 1, 2. Okay, that is, there is a connection between, that is, this function is covering the minterms 1, 2, 28, 29, 31, like that. Similarly, A6, A6. How is this A6? Okay, I will add some number here. Okay, this is after 4. A6, how do you represent A6? A6 can be represented like this. P, W, X, Y. Now we are seeing the ROM as a combinational circuit simply, not as a memory device, just combinational circuit. So A6, it is a one switching function consisting of the minterms C0, 1, 2, 3, and in between we don't know. So like this, okay, 0, 1, 2, 3. 0, 1, 2, 3. We don't know here in between. So like that. Or you can take A4, A4, or let us say A1. Okay, how is A1? A1, A1. You tell me from this. So wherever cross are being shown, that is this minterm 2, minterm 3, minterm 29, minterm 30 are being covered by the output A1. This is one switching function A1. Okay, so 2, 3, 29, 30, 2, 3, 2, 3, and in between we don't know, 29, 30, like that. Okay, so this is also one thing. Okay, so this is combinational circuit implementation point of view. We can represent it like this. Okay, ROM as a combinational circuit. Okay, when ROM is visualized as a combinational circuit implementation, the expressions for A1, A6, A7 are as shown above. Okay, you can mention here. Okay, when ROM is visualized as as combinational circuit, as combinational circuit instead of memory device. Instead of memory device. Just a minute, please. The outputs can be treated as switching functions. That's all. Let us solve one example problem with the help of ROM. Okay. Let us design one combinational circuit. I will give you one example. Design a combinational circuit using a ROM. Design a combinational circuit, CC and a combinational circuit using a ROM. The circuit is like this. The combination circuit, it accepts a 3-bit number and generates a square of the number. That is, if you given 2, it will provide 4. If you given 3, it will provide us 9. If you provide 4, it will give us 16. If you provide 5, it will give us 25. So it is a square circuit square. Okay. So design a combinational circuit which provides a square of the given number. Okay. So you can mention here we are mentioning the combination circuit like this. The circuit. Okay. Here the design a combinational circuit using a ROM. Okay. The combinational circuit. Okay. The circuit accepts a 3-bit number and generates an output binary number. Equal to the square of the input number, binary number that equal to the square of the input number. Itlanti combinational circuit we want to generate. Okay. First of all, what is the truth table for the combinational circuit? First of all, 3 input number ante manaki suppose we have this circuit. It ఏమంటున్నాడు 3 input number ఇస్తున్నాము A0, A1, A2 something 3 input number. So output square రావాలి. ఇది కూడా బైనరీలోనే అవుట్పుట్ స్క్వేర్ రావాలి. ఓకే, స్క్వేర్ ఆఫ్ ది ఇన్పుట్ రావాలి అంటే లైక్ దిస్. ఇప్పుడు A0, A1, A2 ఇది ఉంది. Just I will try to finish as well as possible. చూడండి. సో మనకి ఏముంటుంది కాంబినేషన్ 0 0 0. సో 0 1 1 0 1 1 0 0 0 1 1 0 1 1. రైట్. సో ఇక్కడ లాస్ట్ 7 అంటే 49 కదా బాబు. Square of the 7 means 49. So how do you represent 49? So how many bits are required to represent 49? 49 కావాలి అనుకో. అది జస్ట్ ఫర్ ఐడియా ఇక్కడ ఇస్తాను. 1 2 4 8 16 32 మనకు 49 రావాలి అంటే ఏమేమి ఉండాలి? ఇక్కడ 32 ప్లస్ 16 48 ఇది రావాలి కదా. సో ఇది 49, రైట్? దిస్ ఇస్ 49. సో మనం ఇక్కడ ఎన్ని బిట్స్ మినిమం రిక్వైర్డ్? 3 or 6 బిట్స్ రిక్వైర్డ్, రైట్? సో ఇక్కడ వేసుకోండి 6 బిట్స్. So 6 bits to draw outputs. B5 ఇట్లా వేసుకోండి, B4, B3, B2, B1, B0. So 6. So 49 means here this is 1, this is 1, 0, 0, 0, 1, like this. Right. Like that, fill up the entire table. Just 2 minutes I am giving break. Think of the problem and fill up this table in your notebook. So 0 means here it is 0. 1 means 1. Square of 1 means 1 only. Square of 2 means 4. Square of 3 is 9. How do you write 9? Okay. Like this. Next 4. This is 16. Square of 4 is 16. 16, how do you write? Next, this is 6. So 36. Square of 6 means 36. How do you write 36? 32 plus 4. See here. 36 means here 32 plus 4. No? That is the 1 0 0 1 0 0. 1 0 0 1 0 0. And sorry, this is 5, no? No, 6. No, this is 4. This is 5, no? 5 means 25. 25 means here 25. How do you write 25? 1, 16 plus 8, 24. Here, like this, okay? 0 1 1 0 0 1. 0 1 1 0 0 1 0 0 1. This is 5, 25. Next 6, square of the 6, 36. 36 means 1 0 0 1 0 0. So like this. This is the truth table for the given combinational circuit. right? కొంచెం క్లారిటీగా ఇక్కడ రాలేదు కదా. I will write this properly. 110 7 means 110011001100. This is one like this. Right. This is 0. Right. So this is 1. I'm trying to write neatly. Okay, to add confusion. Okay, so this is a combinational circuit whose truth table is shown here according to the problem statement. Okay, like this. So here these are the B0, B1 like that. Okay, so B5 outputs and the outputs with inputs. Right. So this is our combination. So we want to implement this combination circuit with the help of ROM. With the help of ROM. So here designing a combination circuit with the help of ROM is very, very easy. Simply we have to specify the truth table, that's all. So in this one important point is there. See here B0 is always same as A0. See, in this case, after observation of this truth table, B0 is found to be equal to A0. See here. So B0 can be generated just by establishing a connection between A0 and B0. That's all. That means you can reduce the number of outputs. Similarly, B1 is always equal to 0. See here, B1 is always equal to 0. Okay, constant. That's all. This output should be fixed to some logic 0 state. That's all. So 2 among the 4 outputs are 2 among the 6 outputs are decided. Right. Next. Right. So remaining only 4 outputs. So we can mention simply, we can reduce the truth table like this. Okay, reduce the truth table. I will add some more pages here. Right. Now finished. So I will redraw another circuit reduced to truth table. So A0 Yeah. Once again, I will draw this one. So finally, this can be reduced to A to A1. Oh. Hello? No, hey Baba. Someone shouted. Next. So here, next, this is B5. B5, B4, B3, B2. So B0, B1 can be neglected. So like this. So here it is 0, 0, 0, mic 0. Just a minute. So remaining 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. So here fill up as it is 1, 0, 0, 0, 2 zeros. 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. That's all. This is the reduced truth table of the ROM. Same. Okay. So this is the ROM truth table, right? Actually, okay. Required ROM truth table. That's all this is. Oh. So once you have the truth table, you have the device, entire thing. Okay, design itself is over. Okay, so what is the meaning here? You require a 3 input RAM and 4 output. You require a ROM with 3 inputs and 4 outputs. That's all. So how do you specify here? Okay. So the diagram will be like this accordingly. So I will close it within 2 minutes. So the diagram will be next. So you require simply so 3 inputs means 2 power k and 2 power 3. That means 8 by 4 RAM and so here we require simply inputs and 6 outputs. So can write like this. B0, B1, B2, B3, B4, B5. So for B0 is nothing but A0 only. Okay. So here we have, this is A0, this is A1, this is A2. So A0 is simply can make a connection like this. A0 is simply equal to B0 like that. Similarly, B1 is simply how do you get B1? B1 is simply one constant is provided. Okay, B1 is equal to 0. Okay, so that's all. So this is the ROM block diagram, and here you can mention like this. This is a 8 by 4 ROM. That's it. Okay. So this is the block diagram. That's all. So truth table, according to the truth table. So inside, if you want to draw the its inside logic diagram, so that is left as an exercise for the student. So according to this truth table, you have to make the connections. That's all. Okay. We call it. I will show you. Now it's 4:59. So it is left as an exercise for the tomorrow's class. I will this. I am giving you as an exercise. Now you provide me the internal logic diagram, that is in terms of decoder and OR gates. You draw for this problem. You show me the connections. What should be the connections according to the your ROM truth table? You take the help of this one. Okay. Tomorrow I will ask in the classroom. Okay. Now I will note down the absentees roll numbers. Okay. Okay. If you right. Take this as an exercise. Okay, please provide internal logic diagram until like this. What type of diagram I am asking you? Like this. This is called internal logic diagram of the ROM. అదనమాట. అంటే ఇదేమో పర్టికులర్ ఈ ROM కు ఇచ్చానండి. దీని ట్రూత్ టేబుల్ ఏది ఇక్కడ ఆల్రెడీ కొంత దూరం వెళ్ళిపోయింది. దీనికి ఇది ఫర్ దట్ పర్టికులర్ ట్రూత్ టేబుల్ for that particular ROM truth table. So according to this truth table, you are given this logic diagram, internal logic diagram, this one. Okay, like this. Now you have to provide me an internal logic diagram for this circuit. Okay, 8x4 ROM. What kind of circuit? This circuit is producing square of the number. Okay, just once again I will close just for clarity purpose. Just for clarity, what is actually here? This is that is it is 0 and what? 1, 2, 3, 4, 5, 6, 7. So ఇక్కడ మనం ఏం చేస్తున్నాం అన్నమాట అంటే మనం ఇక్కడ we are mentioning as, so this is 0, 1, this is 2 అంటే ఇది 4, ఇది 9, this is 16. So this is 16, 25, 36, 14. This is 40. 14. డెసిమల్ ఈక్వివాలెంట్ జస్ట్ ఇక్కడ వేసినాం అన్నట్టు మనం. సో ఇదేమో ఇన్పుట్స్, ఇది ఇన్పుట్స్, ఇది అవుట్పుట్స్. సో ఇన్పుట్స్, ఇన్పుట్స్, అవుట్పుట్స్. ఓకే, ఇన్పుట్స్ A1 A0 A1 A2, outputs B0 B1 B2 B3 B4 B5. So like this. So this combination circuit is specified by its truth table. Okay? Right. I will upload this one. I will note down the absentees. Okay. Roll numbers. Roll number 62, absent.